Okay, this video is on what I'm calling dy area. I don't know that it's anywhere else, but it's just a different way of thinking about the area. And so the first thing we're going to do is remember what we tend to remember, and that's if I have a function f, whatever it passes the vertical line test, and I want the area from A to B. So I'm talking about this area here between the function and the y-axis. We write the integral from a to b of f of x dx. Okay, so everything that we've done up until this point has been based on that. Now, what we're going to be looking at today is what happens when we know more about the y than the x's. So I'm going to make up a function f again, and I'm going to say we know about the y-axis from A to B. So I'm talking about this area trapped between the function and the y-axis. Now, when we write that integral from A to B, our variable is no longer x because we are measuring using the y-axis, so we are using f of y dy. We're going to use this concept a little more when we talk about volume in our next unit, but for right now, just getting the area with this, that's the idea. Okay, so let's start with an example. We want the area bounded by f of x and g of x in the first quadrant that is also bounded by the y-axis. So let me take a moment to draw that. Okay, so f of x is a parabola turned upside down, moved up 12, and so that would be this black one that I have here, f of x. And then g of x is our exponential function moved down 1. And normally our exponential function goes through 1, but if we move it down 1, it's now going to go through 0. So both of these are toolbox functions you should be familiar with. And we are going to want to find the area bounded by those and the y-axis. So that is this amount right here. Now, you're looking at that and saying, yes, I already know how to come up with this area. It's the integral from whatever, 0 to this amount of the top minus the bottom. And yes, you can find this one out this way. But for the purpose of practicing this dy area concept, we are going to do something a little bit different. If you kind of turn your head sideways or turn your paper sideways, from 0 to about this point right here, you have the g of x function and the y-axis, and then from that point to 12 you have the f of x function and the y-axis. And so you're going to have to end up adding this area to this area. Well, where do those meet? Let's find out. So I want to find the intersection point. I'm just going to graph these using my calculator to help us out. So I'm going to put f of x into y1 and g of x into y2, and then graph it and calculate the intersection. So pause and do that. Alright, our intersection point right here is the point 2.133, 7.447. And so since we are talking about the y-axis over here, I mean, I'm obviously not drawn to scale, but the y value is what would be on the y-axis. And so I'm going to do the integral from 0 to 7.447 of the g graph, but I'm needing to do it dy, so I'm going to come back. This is just a thought right here. Plus the integral from the 7.447 to 12, and this time it's with the x, or excuse me, the f of x and the y-axis, but again we're wanting to use y variables, which we'll talk about in just a minute. So this is a general thought process of what's going to happen. Now, when I say we're going to use y variables, that means that I can't just say negative x plus 12 and have a dy here, because I would have x's in my function and y over here in my integral. You can't have mismatched variables. So I'm going to take the g function and I'm going to solve it so that my variable is y. So the first thing I have to do is think of g of x as y, and then I have to get the x by itself. So it's kind of finding the inverse here. So I'm going to add 1, and then to get to that x I have to natural log both sides. So natural log of y plus 1 equals x natural log e, and those cancel. So x is the natural log of y plus 1. So this is my g in terms of y. I'm going to do the same thing for f. So my f of x equation is negative x squared plus 12. I'm going to think of that as y, and then solve for x. So subtract 12, divide by negative, and then take the square root. And so this, again, I'm thinking of as my f. So on the picture, when I'm thinking of this graph, I'm thinking of negative y plus 12. When I'm thinking of the green graph, I'm thinking of natural log of y plus 1. But now I've already set up that idea in my mind. I just need to put the g and the f equations in. So I'm doing the integral from 0 to 7.447 of the g, which would be natural log of y plus 1 dy. And I'm going to add that to the area from 7.447 to 12 of the f, which is the square root of negative y plus 12 dy. And I'm going to use my calculator and do math number 9 to put these in and add them together. And if you do that correctly, you should get 17.054, which is the same thing that you would get if you had used the x that we were talking about doing the top minus bottom. So if you want to check it, you would check it using x's from 0 to 2.133 of the top minus bottom in terms of x. So negative x squared plus 12 minus e to the x minus 1 dx. So if you plug that in, you should get that same thing. But again, today we're practicing the dy area, so I want you to do it in terms of dy. If you need to check in terms of x, you can. Sometimes dy is actually the only option for you. You'll see some weird graphs that happen sometimes, and dy is a much better option than trying to do dx. So let's go on to another example. Okay, our second example, we're going to use the same equations. We're just going to find a different area. So we're in the first quadrant still. We're going to be bounded by f, g, and now the x-axis. So let's look back at what that graph looks like. If you'll remember, our f is an upside-down parabola that's been moved up 12. So something like this. And our g was an exponential function that's been moved down 1. So something like this, if it'll stay. Okay, and then we had already found the intersection point to be 2.133, 7.447, and marked that on our y-axis. And we had already figured out what these equations were in terms of y. So this one was negative y plus 12, and the green one was the natural log of y plus 1. Okay, so we had all that. Let's not overthink it. Let's look at what area they want. They want first quadrant bounded by f, g, and the x-axis. So the x-axis being down here, we're talking about this area here. And again, this is something I could break up right here and do a dx from here plus a dx for here. But because today I'm practicing dy, I want to think about it sideways. And if you turn your paper sideways, in relationship to the y-axis, the black one is on top and the green one is on the bottom. So I'm going to be doing the integral from 0 to 7.447 top minus bottom, which would be the f minus the g in this case. But again, I want it in terms of dy. So since I've already figured out those f and g's in terms of y, I can actually just plug in now. I've done most of the work already. So my f would be the square root of negative y plus 12, and the g would be the natural log of y plus 1. I'm doing top minus bottom dy. And really, when we turn sideways and we think in terms of dy, it's more like right minus left. But I still say top minus bottom because I turn my head to think about it, but that's up to you. So now this is again something I would type into my calculator and use math number 9. Make sure you type it just like you see it, and if you do it correctly, you should get 10.659. So that would be your dy area for this. If you want to check it using x's, it would be the integral from 0 to 2.133 of e to the x minus 1 dx plus the integral from 2.133 to, I would have to find what that is. I'm going to say b for right now. Whatever that number is where we intersect the x-axis with the f, of the negative x squared plus 12 dx. And again, it should give you that same amount because it's the same area we're talking about. We're just figuring it out in two different ways. But today I want you to practice that dy area. And that concludes this lesson.